Hello, it's Math 145, day 14. We're talking about lesson 11, solving triangles. This means that we use the law of sines and the law of cosines that I've put on the screen as a reminder to find missing quantities in a triangle if we're given enough information that nails down what that triangle is. And this was way back at the beginning of the semester that I've gone through the possible combinations of clues or data that you need to know about a triangle so that it's nailed down. And last time in lecture, I've already done the case that you're given the three sides of a triangle. This has a code name. This is called the case SSS. And now I'm going to do an example in where we're given two sides and the angle in between. Two sides and the angle in between. How do we proceed here? So it's always standard labeling. The lowercase letters are the sides and they are opposite the vertices, and the uppercase letters are also used for the angles at those vertices. So given A is 3, B is 2, that's two sides, and capital C is, let's say, 80 degrees. That determines a triangle, and the question is, find the third side, that's lowercase c, and the angle at A, capital A. Okay. The third side, that is just perfect for the law of cosines in the form which I've written. So c square is a square plus b square. That's 3 square plus 2 square minus 2 times a times b. That's a 12 cosine of 80 degrees. So we get that side C is the square root of 9 and 4 is 13 minus 12 cosine of 80 degrees. Some number. As it is, I would call that form an exact answer. And in some exams, especially if they're face-to-face, let me tell you, I don't want calculators. I'm happy with the answer in this form. Now, what do we do with finding this angle? We can try a rotated form of the law of cosines. And I'm going to have an acronym for the law of cosines. I'm going to write LOC. So you take this law of cosines, and you want to see the cosine of A here. So that means on the left, you want to see A square, lowercase a square. And the two other sides get squared, so b square plus c square. And then subtract 2bc cosine of capital A. That's the way where capital A or its cosine is the only unknown and we will be able to solve that for cosine of A. Should we actually solve it symbolically? That's probably a good idea. So cosine of A, okay, times 2bc, let's go slow, is equal to b squared plus c squared minus a squared. We divide by 2bc and get a formula for the cosine of A. B squared plus c squared minus a squared divided by 2bc. And then we can plug in our numbers. B squared plus c squared, that's 2 squared plus c squared. C squared is 13 minus 12 cosine of 80 degrees minus a squared, that's 9. Big fraction bar divided by 2bc. 2 times 2 times c, which is that square root of 13 minus 12 cosine of 80. Ugh, it's not pretty, but at least it's only numbers, no more unknowns, and we can apply the arc cosine function to both sides. So we get A is the arc cosine of that whole splodge. It's 4 and 13 minus 9, which is 8, minus 12 cosine 80, divided by 4 times the square root of 13 minus 12 cosine 80. And if you hack that into a calculator, it'll come up with some number. I've actually done it, and it gives me 1.1. 0.066 something radians. Okay, we could also have used the law of sines to do the same thing. For the sake of exercise, let me show you how that would have worked. We could have done sine A divided by a lowercase a, which is 3, equals sine 80 degrees divided by c. Solve that for sine A. It's 3 sine 80 divided by c, which is that square root of 13 minus 12 cosine 80. And then apply the arcsine function. That whole thing. And I've got a bit of a problem with that procedure because there are two angles between 0 and 180 that have the same sine value. So knowing the sine value doesn't really nail down the angle. There's two choices for the angle A, and they are symmetric about 90 degrees. One of them is less than 90, the other one bigger than 90. It so happens that the arcsine function agrees with what we got from the law of cosines up there. So it's an angle that's less than 90. And the arcsine function will always give me an angle which is less than 90 degrees. But this would not work if the angle was actually bigger than 90 degrees. How could we tell? Can't tell just looking at the sine function. So one thing is this rule that I talked about last time, that bigger angles correspond to bigger sides opposite them. So if you have an angle which is bigger than 90, it will be opposite the longest side in the triangle. And to write this down, we may need to modify this if A is greater than 90 degrees. So then A would actually be 180 degrees minus this arcsine thing. We're just lucky that in this example, this did not happen. You could detect this by looking at the sides of the triangle. If A is bigger than 90 degrees, because the angles have to add up to 180, A is the biggest angle in the triangle. Bigger than B and C. And well, that's one thing that you can find out by looking at the sides. Are we looking for the biggest angle? But it's still possible that A is just the biggest angle while still being less than 90 degrees. So in that case, I'm thinking there's no way you have to calculate the two other angles and check that they really add up to 180. So I'm going to do another example for that in lecture. But the far easier way forward is just use the law of cosines. Law of cosines will always give you the right angle, no extra thinking required. So that's the first way that I've used that came up with this 1.1066. And I've checked that the law of sines gives the same answer. But generally, if you can help it, use the law of cosines. That's why I did that one first. So far for this example.